You're welcome to Science Spectrum with Don. This would be the 5th part of the second lectures. And of course, in this aspect, we'll explore more on derived units, the quantities, and of course, their dimensions. All right, so we have the derived quantities, more of it. The list could be endless, but we'll explore just a few. Derived quantities, their units expressed in its equivalent base or fundamental units, and of course we have the dimensions, and I could give you the derived units as well. Alright, so let's get started. Now I may need to replicate this here also. Derived physical quantities. We have the units, which could be equivalent fundamental or base units, and they are derived units as well. And we'll talk about the dimension, just a few among the many. All right, I'll start off with capacitance. Capacitance is the ability to store charge for a given potential. And capacitance is defined as the charge over the potential difference, or the charge per potential. Charge is given in a unit coulomb, then potential is given in a unit volts. Charge itself is current times time, and of course potential is joule per second. Joule per second. So this is joule, then the second comes in here, so I have a T squared here. Now if we explore this, current is in ampere. I have second raised to power 2. Then joule, that's the unit for work. That's work is force times displacement. Force is Newton, that is kilogram meter per second squared. And I have displacement of distance. This gives me a square here. So this would be, I have this term will be down, so I will invert this. I have this, then this is just second raised to power 2. And of course, if I would do the mathematics clearly, I could express potential, that's capacitance, as charge per volts. Charge is ampere second. Potential is joule per coulomb. Joule itself is kilogram squared meter per second squared, first time displacement. Then I have a coulomb downstairs, that is per ampere per second, because ampere second is the same as a coulomb, but I have to invert this downstairs. So this becomes kilogram squared meter. I have second raised to power minus 3, then I have per ampere. That's for the volts. So I have to bring now, this time I have kilogram meter squared, this raised to power minus 1. And of course, to get the job done, everything downstairs I will invert it. So I have ampere second, I have per kilogram per squared meter, second raised to power 3, then of course I have just ampere raised to power 1. So I have ampere raised to power 2 here. So this time becomes per kilogram, then I have per squared meter, I have ampere raised to power 2, then I have second raised to power 4. And of course, this is given by the unit coulomb per volt, and of course we use the unit farad for this. Alright, now I could write its dimensions to be m for mass, this is raised to power minus 1, L minus 2. This is current is I, that's the dimension raised to power 2. Then time is T raised to the 4th power. Alright, now aside from capacitance, let me talk about other derived quantities like resistance. The resistance the resistance, electric resistance on, let's say, a body, could be a conductor or an insulator. So resistance from Ohm's law, V is equals to IR. I could divide both sides by the current. So resistance would be volts per ampere. Potential divided by the current. Now potential is simply joule per coulomb, and we got this joule per coulomb, then per ampere. Then I have, now since it's downstairs, I was taking another, so this becomes ampere raised to power minus 2. So resistance would be kilogram, meter raised to power 2, second raised to power, oh, this is here, minus 3, ampere raised to power minus 2. So this is volts per ampere. Alright, now we use the derived units to be ohm. So one of these is the same as 1 ohm. Alright, now the dimension would be M for mass. Then we have L raised to power 2, T raised to power minus 3. Then we have I raised to power minus 2. Now we have electric conductance. Electric conductance is simply the inverse of what you have here. The inverse of this, we call that the CMN. So this is the inverse of this. I'll flip this over. I have this. I have this. So this is the same as ohm raised to power minus 1. Or we use the derived units, which is the CMN. And of course the dimension will be M to power minus 1, L to power minus 2, T to 3, then current, that's I raised to power 2. And of course we have resistivity. That's given in ohm meter. So if it is ohm, I'll stick in the meter here. That makes this term with meter raised to the third power. So this will be kilogram, meter raised to power 3, this, then I have this. So this is the same as ohm meter. That's the need for resistivity. And of course we have other derived quantities. Aside from resistivity, we have electric conductivity. We have conductivity, which is usually the inverse of resistivity. So I'll just flip this over. So I have per kilogram, I have per cubic meter, second raised to power 3, and I have ampere raised to power 2. And this is the same as ohm meter all raised to power minus 1. That's the need for conductivity. And of course we have for inductance, self-inductance, the ability of a circuit to fight the magnetic flux that it produces itself. So inductance, with the symbol L, but I wouldn't necessarily write out the symbols since we run out of symbols in physics. So inductance is simply the proportionality constant that relates the magnetic flux to the current. So I could replace with an equal to with that constant. This constant is the inductance. So if you divide out both sides by the current, you figure out that inductance itself becomes the ratio of magnetic flux to the electric current. And of course, flux itself is simply the amount of electric field, of magnetic field that penetrates a surface. So that is, electric is Tesla, then the area it penetrates is in square meter, then divide by the current. Current would now be in ampere, per ampere, since it's downstairs. So Tesla itself, I may need to rewrite this. Then Tesla itself is Newton second per coulomb per meter. This is Tesla. Then I have this now, meter raised to power 2, I have per ampere. Now you agree with me that I may still keep this Newton second. We know that coulomb is ampere second, so this is ampere second inverted. Since coulomb is inverted, I have this. Now minus 1 plus 2, that gives us m raised to power 1, and I have per ampere. And of course the second here, Second times 1 over second, definitely this is gone. So I'm left with Newton per ampere, meter raised to power 1. Okay, then I have another ampere to power. So this becomes ampere raised to power minus 2. Now Newton itself is kilogram meter per second squared. So I have a meter here. This becomes a square meter. Then I have per ampere raised to power minus 2. That's ampere raised to power minus 2. So inductance would have its units expressed in the fundamental units as kilogram meter raised to power 2, second raised to power minus 2, ampere raised to power minus 2. And of course, this is also Weber, which is the product of Tesla times square meter. So this is Weber per current is ampere per ampere. But of course, we use the official derived units to be Henry for self-inductance. And of course, the dimensions could be m, L raised to power 2, T raised to power minus 2, then we have I raised to power minus 2. And of course, there are lots of these more to explore. You have heat capacity. Heat capacity, it becomes specific heat capacity when we are particular about a given unit, which could be a gram or a kilogram. So we'll talk about heat capacity. Heat capacity. Heat capacity has the symbol little c. Heat capacity, we could get it from the proportionality constant that exists between amount of heat energy you pump in or you take out, okay, given for a given mass, okay, and the temperature difference. So this is that constant of proportionality, that is heat capacity. So we could divide through by m delta t. We could divide through by m delta t. So write in your own very eyes, you could see that heat capacity would be joule. Kilogram is downstairs, that's per kilogram. Then we have per Kelvin, this is downstairs. But joule itself is unit for work. So that is force times displacement. Force is kilogram meter per second squared. Displacement is in meter. This becomes a squared. Then we have this term left. We have per kilogram, we have per Kelvin. Kilogram would go in per kilogram. So all I'm left with now would be in meter raised to power 2, second raised to power minus 2 per Kelvin. Or we'd say, when expressed in terms of its derived unit, this would be joule per kilogram per Kelvin. Alright, now the dimension for this would be L raised to power 2, T raised to power minus 2. Then for temperature, that is Kelvin. The symbol is theta minus 1 is dimension. And of course, this is for heat capacity. And of course, the list could go just on and on and on. Now, for conductivity, I'm going to leave it out to fill up this, but I will do it. This is m for mass raised to power minus 1, L raised to power minus 3, T raised to power 3, then we have I raised to power 2. These are a few examples of the many more of the derived quantities, their SI units, derived units, and their dimensions as well. Alright, for the sake of time, I need to wrap it up here until the subsequent lectures in our forthcoming bulletin. Alright, if you're new to this channel, you may want to like, share, and subscribe for more content as it evolves gradually. Thank you for tuning in.